So this is the third section of chapter 4 on recurrence relations, and here we're going to be looking at solving a second order recurrence relation. Now, solving a second order recurrence relation is finding this closed form. Yeah, so that means the same thing. So it's a form of a recurrence relation, which means that we can find any term in a recurrence relation. We don't need the previous term or the previous two terms. So we're most likely to see a recurrence relation written like this. Un, basically to find the next term, we need to do some multiple of the previous term plus another multiple of the term before that and add some sort of function of n. So it could be written like that, or it could be written so that we actually have the function g of n on the other side of the equal sign. So you could have a recurrence relation written like this: un plus a un minus 1 plus b un minus 2 equals g of n. So we don't need to rearrange it to make it look like the first form here. We just keep it like this. Now all of these little subscripts, they may be 1 or 2 higher. So we could have for our subscripts, instead of n here, we could have n plus 1. So I'm just going to write down what the subscripts could be. So this could be n plus 1 here, which means that this would be n and this would be n minus 1. Or it could be that the subscript here for u could be n plus 2. So this would be n plus 1 and this would be n. Okay, so our recurrence relations could be written in any of those forms. So now, just like a first order recurrence relation, we have homogeneous and non-homogeneous recurrence relations. So let's have a look first of all at the homogeneous recurrence relation, second order recurrence relation. This is where g of n is equal to 0. So how do we solve these? Well, let's just write down what this form would look like. So we would have un equals a un minus 1 plus b un minus 2. Now these numbers could be, this could be n plus 1 here, n minus 1, or it could be n plus 2 here, n plus 1 and n here. All these could be different letters and may not necessarily be u's here. They may be different letters, but the process is the same. What we're looking at is these coefficients here of the previous term and the term previous to that, and we're going to use those two values of a and b to form something called an auxiliary or characteristic equation. So we form the auxiliary, or it can be called characteristic equation. And this auxiliary or characteristic equation looks like this: r squared minus AR. Now this A is the A that comes from here, the coefficient of this term here, minus B, and this B is this coefficient here, and that equals to 0. And we're going to solve that, and let's just put this in blue. When we solve that, we're either going to have either two real roots, one real root, or basically two repeated roots, or complex roots. And depending on the types of roots we get, will determine what the general solution of the homogeneous second order recurrence relation is. So we will solve this characteristic equation, find its roots, and I'm going to call the roots alpha and beta. So what if we have two real roots? So two real roots. So we'll have roots alpha and beta. So what the general solution is going to be, it's going to be of this form: un equals a times alpha to the power n plus b times beta to the power n. So a and b here are arbitrary constants, and we'd work out these arbitrary constants if we needed to find the particular solution. Okay, so what if we've got one repeated root? So I suppose what I'm going to do here is say, right, these roots are alpha and beta. So here the one repeated root is just alpha. So that would be un equals, and then in brackets we're going to have a plus bn times by alpha to the power n. So that's what the general solution would look like if we had two repeated roots. Now if we had complex roots, two complex roots, now we're always going to have complex roots because they come in pairs. They're going to be conjugates of each other. Now, first of all, these roots, alpha and beta, can be written in two forms. So we could have a root as a plus ib and beta as a minus ib, or we could have our complex roots written as in exponential form. So it could be re to the power I theta, and then the other root beta equal to re to the negative I theta. And this means that we have two ways in which we can write our general solution. So we can write our general solution using the argument and modulus of the complex number. So that would be un equals r to the power n, so that's the modulus to the power n, times by a cos n theta, so theta would be the argument, plus b sine n theta, so again theta would be the argument. Or we can write our roots, so let's just put the word or here, in this form: un equals a alpha to the power n plus b beta to the power n. So you'll notice that actually this is the same form as the two real roots, and where we've got alpha and beta here, we would just put our complex roots. Now we can write them in either form, so a plus ib here, a minus ib here, or the exponential form here and here. So we've got two ways in which we can write the general solution when the answers are, or the roots are, complex. Right, so what if g of n is not equal to 0? Then we have something that's non-homogeneous. And so let's look at the method for solving a non-homogeneous second order recurrence relation. So let's start with the form of a second order non-homogeneous recurrence relation. So it'll be the same as the homogeneous, but then we'll have this function of g, or function of n, on the end. Now, as I said before, this may be written in one of these forms here. We tackle it in the same way, so we don't rearrange this like the second purple one to look like the one at the top. We keep it in this form, but you know, what we're interested in, what we want to pick out, is a, b, and this function of n. So the first thing we need to do is to solve the homogeneous part, which is this part here. We find the general solution to that by using this method over here, and that will give us what we call the complementary function. So complementary function. Then we're going to look at g of n and the form of g of n, and use that to help us find the complementary function. Sorry, not the complementary function, the particular solution. So this table here will help us to decide what form the particular solution is going to take based on the form of g of n. So if g of n is just a number, a constant, then our particular solution is going to be the form of lambda. If g of n is some sort of linear function, let's say 3n minus 2, then we try lambda n plus mu as the particular solution. And if g of n is a multiple of p to the power n, so let's say it's something like 5 times 2 to the power n, then we try lambda times 2 to the power n. So notice that p to the n that's here appears over here. We just replace the constant here with lambda. Now we would sub whatever form of the particular solution, we sub this into the recurrence relation, the original question, to find the values of mu and lambda. Now it may be that we have a particular solution of the form lambda, for example, and already in our complementary function we already have something that's of that form, so we've got a constant in there. Or this particular solution here, we've got something of that form, we've got some sort of linear expression here in the complementary function. Now if that happens, what we need to do is to multiply the particular solution by n, if that's the case. So we'd have lambda n here, lambda n squared plus mu n, and then here we'd have lambda n p to the power n. Or it may be that actually once we've multiplied by n, that still occurs somewhere in a complementary function, so we times it by n again. So you'd have lambda n squared, lambda n cubed plus lambda n mu n squared, or lambda n squared p to the power n. So always be on the lookout. Does the form of particular solution that I've chosen appear a form like it in the complementary function? If it does, then you either multiply the particular solution that you've tried by n or by n squared. So what we'll have is our complementary function, let's just call that CF, and our particular solution, which we've called PS. So our general solution is equal to the complementary function, which we've found using this method, plus the particular solution, which we found using this method. That'll give us a general solution. Now if we want a particular solution, or what we can call the final solution, so that we don't end up sort of mixing it up with this particular solution, then all we do is we substitute in any initial condition. So you might be told u1 equals something, u2 equals something. So we'll just write down here, sub in initial conditions to find value of arbitrary constants. Okay, we'll just put const there because I've run out of space. And these arbitrary constants, they will be the values of a and b that we have here that we got from a complementary function. Okay, so in this question here, it says that we need to verify that the following particular solutions satisfy this recurrence relation. So we don't actually need to solve anything. All we need to show is that these different values of un satisfy this given second order, and it's actually a homogeneous, there's no function of n here, second order recurrence relations. This is a homogeneous type. But as I said, we're not solving it, we're just verifying, we're proving that these are solutions. So how do we do that? So in part A, we're told that un equals 3n. So that means that un minus 1, if we change for n minus 1 the other side, is 3n minus 1. And then un minus 2 will be 3 and then n minus 2. So we just substitute n for n minus 2. And then what we do, we substitute them into here, and then we should get 3n as a solution. So now substituting them in, we're going to have 2 times un minus 1, which is this, so 2 times this. So 2 times by 3n minus 1, then minus un minus 2, which is this. So we need to subtract 3n minus 2. And we're just going to multiply this out and we should get 3n. So let's have a look. So I'll have 2 times by, and then in the brackets 3n minus 3, minus, and then 3n plus 6. So that would be 6n minus 6 minus 3n plus 6, and that leaves us with 3n. So that verifies that 3n is a particular solution to that recurrence relation, because that's what we get, yeah, given those bits of information. Okay, so part B, we've got un equals 5. Now that means that un minus 1 is also 5, because the function isn't a function of n, so changing n is not going to make any difference. So they're all going to be 5 there. So just like before, we're going to substitute these values into this recurrence relation, see what we get. So we've got 2 times by un minus 1, which is just 5, minus un minus 2, which is just 5. So that's 10 minus 5, which is 5, and that equals un. So that, like the previous one, verifies that 5 is also a solution to this recurrence relation. And then the last one, we have un equals 3n plus 5. And notice that 3n plus 5, this is a combination of these two put together. So un minus 1 will be 3n minus 1 plus 5, and un minus 2 will be 3n minus 2 plus 5. Now, just like before, we're going to substitute them into this. So we have 2 lots of un minus 1. So that's 2 lots of 3 times by n minus 1 plus 5. And then we minus un plus 2, which is this. So that's, put this in brackets, 3 times n minus 2 plus 5, and we subtract that. Right, so let's see what we get when we expand the brackets. So we'll have 2 lots of 3n minus 3 plus 5, and then in the second brackets we will have 3n minus 6 plus 5. Right, well, what does that give us? Well, 6n, and then minus 3 plus 5 is 2, times that by 2 will give me 4, and then I'm going to minus 3n, and then I've got negative 6 plus 5, which is negative 1, then I've got negative 1, which is plus 1, so that will give me a final solution of 3n plus 5, which equals un, which again verifies that 3n plus 5 is a solution, a particular solution to this recurrence relation here. So in part A, we need to find a general solution to this second order recurrence relation. It's homogeneous. So that means we form the characteristic equation, the auxiliary equation, which is going to be I squared minus AR minus B equals 0. So let's do that first. So auxiliary, or the characteristic equation, is R squared minus A. Now A is 2, so it's the number in front of the un minus 1 term, and 8 is going to be B. So it's R squared minus 2R minus 8 equals 0. So now if we solve that for R, so we want two numbers that multiply to give negative 8 and add to give negative 2, so it's going to be 4 and 2. So if I want negative 2, I want negative 4 and plus 2. So the roots are R equals 4 and R equals negative 2. Now, since we have real roots here, it might be worth just reminding ourselves what the general solution is. It's always of this form: un equals a alpha to the power n plus b beta to the power n, where alpha and beta are our roots. So they're going to be 4 and negative 2. So we can go straight and write our general solution as un equals a, our arbitrary constant, times by alpha, which is 4 to the power n, plus b, our second arbitrary constant, times by the second root, which is negative 2 to the power n. So there's our answer for part A. This is the general solution. In part B, it says verify that your general solution from part A satisfies the recurrence relation. Now, if it satisfies the recurrence relation, it basically means that I can substitute this into my original recurrence relation and get un. So I need to do 2 lots of un minus 1. So I need to change these n's to n minus 1, plus 8 lots of un minus 2, which means I need to replace these n's with n minus 2, multiply that all out, and hopefully all of that just becomes un. Right, so if we substitute in, so we'll get 2 lots of, so this and this n need to become n minus 1, because we're getting 2 lots of un minus 1. So that would be a times 4 to the power n minus 1 plus b times negative 2 to the power n minus 1. And then we add to that 8 lots of the same expression here, but now with n minus 2, because it's un minus 2. So that's going to be a times by 4 to the power n minus 2 plus b times by negative 2 to the power n minus 2. So we'll start by expanding the brackets. So we'll have 2a times by 4n to minus 1 plus 2b times by negative 2 to the power n minus 1 plus 8a times by 4 to the power n minus 2 plus 8b times negative 2 to the power n minus 2. Now the only way we can simplify this is to make sure that these powers are the same. So at the moment we've got n minus 2. So if it's possible to multiply this expression here by 4, another 4, then it will increase the power by 1. If I can multiply this by 4, or sorry, by negative 2, I can increase the power by 1. So I can make these powers n minus 1. I can do that by making 8 4 times 2, or 2 times 4. So then I could rewrite this expression as 2 times a times by 4 to the power n minus 1. So I've taken 4 out as a factor, multiplied this by a, it will 8 4, and it will increase the power by 1. And here 8 is the same as negative 4 times by negative 2. So I take a 2 out, negative 2 out as a factor, I times it by this, that will increase the power by 1. So let's write down what that will now become. So the first 2 terms stay the same. So 2a times by 4 to the power n minus 1 plus 2b times by negative 2 to the power n minus 1. Then the third term is going to be 2b, because we've taken the 4 out as a factor, times by 4 now to the power n minus 1, because we've just times it by 4. And then plus, actually it's going to be minus, because we've taken that factor out, so it won't be plus, it will be minus 4 times by b times by negative 2 to the power n minus 1, because we've multiplied it by negative 2. We've taken that out as a factor from the 8. Just going to correct this here. That should be an A. You've probably spotted that. That shouldn't be a B. Now what we can do is we can now collect together like terms. You can see we've got 2 of these and 2 more of them. So we've got 4 lots of A times by 4 to the power n minus 1. So we have 4A times by 4n to the minus 1. And then we can also put these together. So I have got 2 lots of this expression minus 2 lots, or sorry, minus 4 lots of that expression. So that gives me minus 2 lots of b times by negative 2 to the power n minus 1. Now this is actually the same as we've got a 4 here, so we can increase that power by 1. So that's the same as a times by 4 to the power n. And then this minus 2, we can times it by that minus 2. So plus b times by negative 2 to the power n. Now compare that to what we said was the general solution. A times by 4 to the power n plus b times negative 2 to the power n. That is indeed un, isn't it? So we've proved it as required. We've proved that, or we verified that our general solution satisfies this recurrence relation that was given. So moving on to part C, it says given that u0 equals 4 and u1 equals 10, what we want to do is to find a particular solution. So we're going to use these to work out the arbitrary constant. So if un equals 4, that means here that we've got n equals 0, and with u1 equals 10, that means n equals 1. So we just substitute these in. So starting with u0, we will have 4 equals a times by 4 to the power 0, because we're using u0, which means n equals 0, plus b times by negative 2 to the power 0. Okay, so what that's going to give us is this equation, a plus b equals 4. Okay, so this is our first of our 2 equations. So now we'll substitute in the u1 equals 10. So that means u1 equals 10 and then n equals 1. So that will give us this equation. So plus b times by negative 2 to the 1. So we now get this second equation. So that's going to be 4a minus 2b equals 10. And what we can do is solve these two simultaneously to work out the values of a and b. Okay, so for example, one way of doing it is to say from my first equation, I've got b or a equals 4 minus b. I can then substitute that into the second equation, so that will give me 4a, so I can do 4 times by 4 minus b minus 2b, so substitute into the second equation, I get this, so that would be 16 minus 4b minus 2b equals 10. So I will get, if I move the b's over to the other side, I'll get 6b, and then move the 10 across to the other side. So 16 minus 10 is going to be 6. So that will give me b equals 1. And then it's very easy then to find a. If b equals 1, then a equals 3. So now I've got my values of a and b. I can now write the particular solution. Just replace these a and b with the numbers 3 and 1. So I'll get a particular solution of un equals 3 times by 4 to the power n, and then it's just 1 for b, so plus negative 2 to the power n. So that completes our particular solution. Right, so on this question we need to solve this recurrence relation. Now we've been given some initial conditions, so that means we're going to be finding a particular solution. So it's homogeneous, so we just need to form and solve the auxiliary or characteristic equation, find the roots of that, find a general solution, and then once we've done that, we can then substitute in these initial conditions and find a particular solution. So the first thing is this auxiliary equation. And the auxiliary equation is going to be r squared minus, now 3 is the value of a in our auxiliary equation, and b, that its value is -2. So we're going to have r squared minus 3r minus -2 equals 0. So be careful, b is -2, we still subtract -2, so that's r squared minus 3r plus 2 equals 0. Now that can be factorized, and that will give us 1 and 2, so -1 and -2. So the roots are alpha equals 1, beta equals 2. So now that we have, or we know how many roots we've got 2 real roots. We know the general form of the general solution, which is going to be un equals a times by alpha n plus b times by beta to the power n. Now in this question, it's all in terms of a, so make sure that we don't use u. So in fact, I'm going to put a here just to remind me, so I don't write u's down when I should be writing a. So just be aware of that. Right, so now we can say that the general solution is going to be not un, but an equals a times by the first root alpha, 1 to the power n, plus b times by the second root 2 to the power n. Now we've got 1 to the power n here, that's just 1. Anything 1 to the power anything is going to be 1. So actually we can just write this as an equals a plus b times by 2 to the power n. So now we can use our initial conditions. A1 equals 5, which means n equals 1, and a2 equals 3, which means n equals 2, and we can use these initial conditions to find the value of the arbitrary constants. So let's start by substituting in a1. So that will mean that a1 equals a times by b, sorry, a plus b times by 2 to the power 1. Now since a to the power 1 is 5, we can just write 5 equals a plus b times 2 to the power 1, which gives us this equation, a plus 2b equals 5. And then we have a2 equals a plus b times by 2 to the power 2. And since a2 is 3, we can write 3 here. So this will give us our second equation, which is going to be a plus 4b equals 3. Now we'll solve these simultaneously, and I've got them nicely written one above the other, so we'll subtract. So maybe if I do the bottom equation minus the top one, so a minus a, 0, 4b minus 2b is just 2b, and then 3 minus 5, well that's going to be -2, so that will give me b equals -1, and then I can easily substitute into here. So let's do that. Let's substitute that into that one. That looks easier. So that will give us a plus 2 times by -1 equals 5. So a equals 5. They've got -2, so that'll be +2. So a equals 7. So I've got the value of my arbitrary constants. So now I can write the particular solution. So my particular solution, all I do is replace my arbitrary constants a and b from my general solution with 7 and -1. So I will have a particular solution of an equals a times 1 to the power n. Now we said it was just our general solution, it can be written like this. It's just going to be 7 plus, well actually it's minus because we said b is -1. So -1 times by 2 to the power n. So we could just write that as an equals 7 minus 2 to the power n. And we'll just highlight that. So we need to solve this recurrence relation here. We've got some initial conditions, so we can find the particular solution. So in our auxiliary equation, a is going to be 4 and b is going to be -4. So we start by forming and solving our auxiliary or characteristic equation. So that will be r squared minus 4r minus -4. So be careful with that. b is -4, you still subtract it. So that gives us r squared minus 4r plus 4 equals 0. So let's see if we can factorize this. So I want plus 4 multiplied to make plus 4 and add to give -2. So -2 minus 2, or you could say r minus 2 all squared equals 0. So this has a single root, which we'll call alpha, which is equal to 2. Okay, since r equals 2, alpha is 2. So what's the general solution when we've got two repeated roots? Right, when we've got two repeated roots, our general solution is of this form: un equals a plus bn times by alpha to the power n. So that's where our root's going to go, where alpha is. So general solution will be un equals a plus bn, so they're arbitrary constants, times by 2 to the power n. Now from here we're going to use our initial conditions to find a particular solution. So we have u0 equals 1, so that means n equals 0. And the other initial condition is u1 equals 1, which means n equals 1. So we'll plug both of these in and write down what the equations are. So let's start with u0 equals 1, which means n equals 0. So that will give us 1 equals a plus b times by 0, n is 0, times by 2 to the power 0. Now all of this is just going to become, well, that's gone. This is just 1, so this just leaves a equals 1. So now let's use the other initial conditions, u1 equals 1, which means n equals 1. Okay, so that will be 1 here, u1, and then a plus b times n, n is 1, times by 2 to the power 1, because n is 1. Now if we do this, what we're going to get is a plus b here. All of that's going to get times by 2, so we're going to get 2a plus 2b equals 1. So 2a plus 2b equals 1. Now we've already worked out that a is 1, so this equation becomes 2 plus 2b equals 1, which means that 2b equals 1 minus 2, which is -1. So b equals -1/2. So now we've got the value of our arbitrary constants, which we can put in here in a general solution to now get our particular solution, which will be this: un equals a, which is 1, plus b, which is -1/2. So actually I'll put -1/2 n here, times by 2 to the power n. So this now here is our particular solution. Okay, so in this question here, we want to find a general solution to this recurrence relation. That's part A, and part B is finding a particular solution, because I can see some initial conditions. So we start by finding the auxiliary equation, and that will be r squared My value of a is 2, so minus 2r, and then the value of b is negative 2, so we need to be careful, it's minus negative 2, so you're always minusing a, you're always minusing b. Remember, the auxiliary equation is of this form, so be careful, watch out. If you get the wrong sign, you could end up with the wrong roots and a totally incorrect general solution. So r squared minus 2r plus 2 equals 0. Now if I look at that and I think I want to try and factorize it, two numbers that multiply to make 2, that's going to be 1 and 2. I can never make them 1 and 2, so this isn't going to factorize. It may be that the roots are not whole numbers, or it could be that the roots are complex. The only way to find out is to use the quadratic equation. So in the quadratic equation, my value of a is going to be 1, b is going to be negative 2, and c is going to be plus 2. Right, so what do we get for our roots? Let's see. So minus b, so minus 2, plus or minus the square root of b squared, so negative 2 squared, minus 4 times a times c, all over 2a, so 2 times 1. Now what do we get from this? We'll have 2 plus or minus, now in the brackets here, we will have 4 minus 8, so it's going to be negative 4, so the square root of negative 4 all over 2. So the square root of negative 4 is going to be 2i. So I've basically got 2 plus or minus 2i all over 2, and that simplifies. If I divide that by 2, so my roots, let's call them alpha. So alpha will be 1 plus I, and beta will be 1 minus I. So I've got complex roots. Now, this question doesn't say which form to write the solutions in, so we're going to write them in both forms. So I've already got it in the a plus ib form, so I want it in exponential form, so I need to know that what the modulus and argument of that complex number is. So I'm just doing like a little sketch here, so I can see where the argument is. Now I can see that the modulus of that is going to be square root of 1 squared plus 1 squared, so that's root 2. And the argument, well, this is an isosceles triangle, that side and that side are the same length. This is 45 degrees, which is pi over 4. So I don't need really to do any calculations, I can see easily what those roots are. So my roots in exponential form will be alpha equals root 2, so that's r times by e to the power I pi over 4. Then the other root will be the same thing, but the argument will be negative I pi over 4. So I now have my roots in exponential form and in a plus or complex number form. So before we put our general solutions down, just a reminder of the two forms that we have if we have complex roots. So one is this form, which uses the modulus and the argument like this. So you can see the modulus here and the argument here, which we have. So we've got the modulus and the argument here. Then the other form, which is written like this, so un equals a alpha to the power n plus b beta to the power n. So actually this is the same form as when we have two real roots, where we have alpha and beta. We could actually use the exponential form of the roots, but we're going to use this form here, yeah, and write both forms. Okay, so let's call this form 1. Okay, so I'll put form 1 or type 1. and here form 2 or type 2. So when we start with form 1, that will be un equals, now the modulus is root 2, so it's root 2 to the power n, and then times by a cos n pi over 4 plus b sine n pi over 4. And then form 2, we'll use the a plus bi form, and that will be un equals a, and then our first root is 1 plus I to the power n plus b, and then 1 minus I to the power n. So when you write your answer, you would use one or the other. So you'd give your answer in this form, or you'd give your answer in this form. Now the question may tell you which form to write it in. If not, you just choose one of those two forms to give your answer in. Okay, part B, and we'll carry on this line down here. We need to find the particular solution where we have u0 equals 1 and u2 equals 2, and we're going to give the answers using both forms. So again, if you were doing a question like this, you would either choose one form or the other. Now I've just spotted that there's a mistake in the book. Here where it says u2 equals 1, that can't be right. That must be u1 equals 2. So not u2 equals 2, but u1 equals 2. So I will just change that to 1 and highlight this here and show that this is an error. This should actually say u1 equals 2. You've got to have two consecutive terms. If you look, these are two consecutive terms. Okay, so these two must be consecutive. So that's an error there. That should be u1, not u2. Right, so let's just write down the u0 equals 1 and the u1 equals 2 for form 2 over here. So remember, the 0 here means that n is going to be equal to 0, and here n is going to be equal to 1, n is 0, and n is 1. Right, so let's start with form 1, which is this form here. Okay, so we'll start by substituting the u1 equals 1 into form 1. So that will give us un or u0, which is 1, equals. So everywhere we see n now, we put 0. So it's root 2 to the power 0 times by a cos, and then n times, or 0 times by pi over 4 is 0, plus b sine. Again, if we've got n is 0, it's going to be sine 0. Now be careful, watch out that cos 0 isn't 0. Sine 0 is, so don't think, oh right, there's a 0, this is all 0. So just watch out for that, that cos 0 is 1. So if we sort of simplify all of this, this is going to be 1, this is going to be 1, this is going to be 0. So all we're going to be left with is that a equals 1. So I'll just put that over here in black. A equals 1, a equals 1, and then forming our second equation, that will be using u1 equals 2. So here we'll have 2 here, and anywhere we see n, we put 1 there. So it'd be root 2 to the power 1, and then a cos. Now this is going to be pi over 4 times by 1, so that's just going to be pi over 4 plus b sine, and then again pi over 4 times by 1, so just pi over 4. Okay, now if we work out cos pi over 4 and sine pi over 4, They're both 1 over root 2 or root 2 over 2. And we've already worked out the value of a is 1. And this is going to be root 2. So let's write down what we get. So we're going to have 2 equals root 2 times by, so a is 1. This is root 2 over 2, or 1 over root 2. So this runs as 1 over root 2, plus b times by 1 over root 2, or 2 over root 2. Right, now if we multiply the brackets, these 1 over root 2's, when we times them by root 2, is just going to be 1. So we just end up with 2 equals 1 plus b times 1. So that's just b. So that gives us a value of b equal to 1. So I'll just highlight those. So these are the values of our arbitrary constants. So now we can write our particular solution, which is going to be un equals root 2 to the power n, and we just replace a and b with 1 and 1, so that's nice and easy. So then we have cos n times pi over 4 plus sine n times pi over 4. And there we have our particular or final solution if we write it in form 1. Okay, so now what we'll do is we'll now give the solution in the form of form 2. So we would do one or the other, not both, but I'm just showing you what you would do if you had either one. So the first thing we're going to do is we're going to substitute the u1 equals 1, n equals 0 into this. So that will be 1 equals a times by 1 plus I to the power 0, because n is 0, plus b times by 1 minus I, again to the power 0. Now anything to the power 0 is 1, even if it's complex. So these will both be 1s, so we'll end up with a plus b equals 1. A plus b equals 1. So let's just highlight that. There's our first equation. So now we substitute in the u1 equals 2. So that will give us 2 equals a times by 1 plus I to the power 1, because n is 1, plus b times by 1 minus I to the power 1. Now, anything to the power 1 doesn't change what we have in the brackets. So basically we will have, and I'll write it this way around, a plus ib plus, plus ia, so I'm expanding the first bracket. Then expanding this bracket here, that will be b minus ib equals 2. Now, we've already got this first equation here, so let's see what equation we get when we simplify this. So to enable me to substitute that into this, I need to collect together the real and the imaginary terms. So the real terms are a and b. That's handy because actually what I've got is a plus b in the first equation. So a plus b, and then the imaginary parts are going to be a minus b, and all of that equals 2. So that makes things fairly straightforward, because then I can substitute this a plus b equals 1 here, so I can just put 1 here. So I end up with 1 plus a minus b times by I equals 2. We'll take away 1 from both sides, so we'll have a minus b, so this imaginary part is equal to 1. Now for this equation to be true, what do I need to multiply I by to get 1? Well, I know if I multiplied I by I get negative 1. So to get plus 1, I need to multiply I by negative I. So that means that A minus B is equal to negative I. Okay, so we'll highlight this. This is our second equation. So now we can solve this one and this one simultaneously to find the values of A and B. So let's start first of all by adding these two equations together or subtracting them. So I've got A plus B equals 1. A minus B equals negative I. So what I'm going to do is, I'm going to add them together. So that will give me 2A equals 1 minus I. So that will give me A equals 1 minus I over 2. I'll take the same two equations again. So A plus B equals 1. A minus B equals negative I. And instead of adding them this time, I'm going to subtract them. And that way I get rid of the A's and find the B's. So I'll have B, that's meant to be a B there, minus negative B, so that's going to be 2B, equals 1 minus negative I, so that's going to be 1 plus I. So that will give me B equals 1 plus I over 2. So I'm now ready to write my particular solution in this form. And notice that my arbitrary constants A and B, so let's just highlight those, are complex, not real. So final particular solution, UN equals A, which is 1 minus I over 2, times by 1 plus I to the n, plus B, which is 1 plus I over 2, times by 1 minus I to the n. So there is our particular solution if we give it in that form. Now you'll probably see that actually the first form, form number 1, is the easier way to do it. It's easier than the second way. So if you had a choice, I would use form 1, unless the question specifically asks that you need to give your answer in this form. So if you have a choice, use this form, form 1, which is this one, the one with cos and sine in, because you can see that the working does work out easier. So here we've got the Fibonacci sequence, which is defined recursively. Don't let that confuse you. This basically means it's a recurrence relation, and it gives us the recurrence relationship here with some initial conditions, and it says find a closed form. Again, don't let that confuse you. That basically means that we want to find a solution. So the first thing we need to do is to form and solve the auxiliary equation. Now the coefficients of these terms here are both 1. So I've got A is 1, B is 1. So I will have an auxiliary equation of r squared minus r minus 1 equals 0. Now this doesn't factorize, because if it did, I'd need 1 and 1 in a bracket, and I'd need a 2 there, which I don't have. So we're going to use the quadratic equation. With the quadratic equation, it means that A will be 1, B will be negative 1, and C will be negative 1. Now you could use your calculator to solve this for you, but it may not give you exact answers. So just be aware that may give you decimals, which is going to make things untidy. So minus b plus or minus the square root of b squared, so it's negative 1 squared minus 4 times a times c, which is negative 1, all over 2a. So what will that give me? 1 plus or minus, so let's do the 1 plus here and the 1 minus down here. The bit underneath the square root, well, that's just going to be 1, and that'll become plus 4. So 1 plus 4 is 5, so we have root 5. And all over 2. So these are my values of alpha and beta. So I've got 2 real roots. Whenever I have 2 real roots, the general solution, it will be a alpha to the power n plus b beta to the power n. So I can now write my general solution as, if I can write the word general properly, let's try again. General solution as u n r. Well, it's not u, it's f. So fn equals arbitrary constant times by 1 plus root 5 over 2 to the power n plus b times our arbitrary constant there, 1 minus root 5 over 2 to the power n. So now we're going to use our initial conditions to find the particular solution or final solution. So I have f1 equals 1, so that means that I will substitute n equals 1. Then the other initial condition is f2 equals 1, and that's going to be n equals 2. Right, so let's do that. So the first one's going to be f1, which is 1, equals, it's going to be a times by 1 plus root 5 over 2 all to the power 1 plus b times by 1 plus or minus root 5 over 2 all to the power 1. So let's see if we can simplify that. Well, we can multiply both sides by 2 and we'll get a times by 1 plus root 5 plus b times by 1 minus root 5 equals 2. So I'll just highlight this. This will be our first equation. Okay, so now let's go for the second initial condition. So we've got f2 equals 1, so I'll have 1 equals to a. Now this time n is 2, so 1 plus root 5 over 2 squared plus b times by 1 minus root 5 over 2 squared. Now, if I use my calculator to work out these bits here, the first part will be, if I square it and it's divided by 2, that will just become 3 plus root 5 over 2, and then the second one will become 3 minus root 5 over 2. So I can times both sides by 2 and I'll get a times by 3 plus root 5 plus b times by 3 minus root 5 equals 2. So this will be my second equation that I'm going to use to solve simultaneously. So I want to solve this one here and this one here simultaneously. Now you might be saying to yourself, well, why not just solve them on my calculator? Well, the problem is I've tried this on the ClassWiz calculator. It doesn't give you exact solutions, it gives you decimal answers. You're probably going to have to go for the CG50, the graphic calculator, to get solutions which are exact. So really on this type of question, we're probably going to have to do it manually. Now that's not a problem, since both of these equal 2, so I can make them equal to each other. So I can say, and I'm going to expand the brackets as well as I do it. Yeah, so I will write down that I've got a plus root 5a, this is from the first equation, plus b minus root 5b equals 3a plus root 5a plus 3b minus root 5b. Okay, so since they're both equal to 2, I've made them equal to each other. Now what happens here is that I've got root 5a, they will cancel out. Root 5b cancel out. So here I just end up with a plus b equals 3a plus 3b, 3a plus 3b. We can take away a from both sides, so we just end up with 2a plus 2b equals 0. Then we can divide both sides by 2 and move the b across, so we've got a equals negative b or b equals negative a. So that's going to be useful, so I'll just highlight that. And now we can use this now and substitute it into one of these two and then go on to find the values of a and b. Right, so if I now take this equation here and substitute this b for negative a, so sub b for negative a, so you can see what I'm doing for negative a, then I will get, and I will expand the brackets again, a plus root 5a. This b is going to become negative a, so I'll have negative a, and then negative a times by negative root 5 is going to be plus root 5a. Root 5a equals 2. Now you can see that that a and that will cancel out, so I'll have 2 root 5a equals 2. 2 root 5a equals 2, divide both sides by 2, divide by root 5, and then I will get a equals 1 over root 5. Now I don't need to do a lot of work to find b, because b is just basically the negative of a, which means that b equals negative 1 over root 5. So on this question we have to go through this process, because unfortunately, unless you've got a big expensive £100 CG50 calculator, you've got a ClassWiz calculator like most of us have, it's not going to give you an exact solution. So now I've got my values of my arbitrary constants a and b. I can then write my final solution, or my particular solution, let's call it particular solution, by just replacing my arbitrary constants with those values. So that will be Fn, I'm going to put Un, Fn equals, so we are taking our general solution here, let's just highlight that, it's lost in the working there, and we'll replace a and b with 1 over root 5 and negative 1 over root 5. So we'll have 1 over root 5 times by 1 plus root 5 over 2 to the power n, and then we'll have minus 1 over root 5 times by 1 minus root 5 over 2 to the power n. So that becomes our particular solution for this equation. Now there's something interesting here, in that this value here, 1 plus root 5 over 2, is the golden ratio. Now you've probably come across that before. If not, search it up and find out what the golden ratio is about. You may already know that with the Fibonacci sequence, as you go further and further in the sequence, if you take a value and divide it by the previous value, you get this number that's about 1.618, I think, something like that, which is this golden ratio that turns up all over the place in sort of mathematics and in sort of artwork, and it turns up in sort of plants and things like that as well. So it's worth searching out and finding out a bit more about this golden ratio. Okay, so we want to solve this recurrence relation. So first of all, it's non-homogeneous, which means to find the general solution, we want the complementary function and the particular solution. So we need to start by finding the general solution to the associated homogeneous recurrence relation. So the associated homogeneous recurrence relation is, now to find the associated homogeneous recurrence relation, g of n needs to be equal to 0. Okay, so if we make g of n equal to 0, then we have an plus 2 plus 4 an plus 1 plus 3an equals 0. Now if we want to find the auxiliary equation, which will be the next thing to do, we need to have the associated homogeneous recurrence relation written in the right form. Now at the moment it's not in the right form. This really needs to be written like this: an plus 2 equals minus 4an plus 1 minus 3an. Okay, so we need to have like the final term we're finding, like un over here. Okay, so auxiliary equation. So let's do that first. So we'll start by writing an plus 2 equals negative 4an plus 1 minus 3an. So I can see my auxiliary equation is going to be r squared. A is negative 4, so minus negative 4 r. And then b is negative 3, so minus negative 3 equals 0. So that becomes r squared plus 4r plus 3 equals 0. So if we solve that, it's going to be 3 and 1 plus 3 and plus 1. So that means that r equals minus 3 or minus 1. So my roots, alpha equals negative 3 and beta equals negative 1. Since I have two real roots, the general solution, if I've got two real roots, is un. In this case, an equals, then it's a times alpha to the power n plus b times beta to the power n. So this will be our general solution, which is actually our complementary function. And it's the general solution to the associated homogeneous recurrence relation. So it's the complementary function of the non-homogeneous recurrence relation. So yeah, our complementary function will be an equals then a times by alpha negative 3 to the power n plus beta, or b times by beta negative 1 to the power n. So let's just put this in a box so we don't forget about it, because we're going to need that in a moment. Okay, the next thing is we move on to the next part, which is looking at the particular solution. So we need to look at the form of g of n. So we can say since g of n is of the form, now what have we got? We've got a constant times by something to a power. Okay, we try the particular solution, or PS, of lambda p to the n. So in this case it will be lambda times by negative 2 to the n. Now we don't need to multiply this by n because there's nothing of this form in the complementary function. There's no negative 2 to the power anything. If there was, then we'd have to multiply this by n, and we'll try lambda n times by negative 2 to the power n. Okay, so this is what a n equals. So this is what we are now going to substitute into here. Now if an equals this, an plus 2 will just be the same thing here, but with n plus 2. An plus 1 will be the same thing, but with n plus 1. So we now substitute that into the original recurrence relation. So an plus 2 will be lambda minus 2 to the power n plus 2 Then we've got 4 lots of an plus 1, which would be lambda times by negative 2 to the power n plus 1. Then we have plus 3an, so it's just plus 3 lambda minus 2 to the n equals 5 times by negative 2 to the n. Right, so we need to solve this for lambda, and the only way we're going to do that is if we make these powers the same. Now, how do we do that? Well, here n plus 2 as a power is the same as negative 2 to the power n times by negative 2 squared. So actually, I'm going to take out a negative 2 squared and then also have negative 2 to the n. With this one here, I'll do the same thing. I'll take out a negative 2. So this is the same as negative 2 times by negative 2 to the n. That way I can get all of the powers the same. Right, so if we do that, that will give us, so negative 2 squared is 4, so I have 4 lambda times by negative 2 to the power n. Then here I'm going to have negative 2 times by 4 is going to give me negative 8 lambda negative 2 to the power n. And then the last term we don't need to change, so that would be 3 lambda negative 2 to the power n equals 5 minus 2 to the n. So now we've got all of the powers the same. Next thing we can do is divide everything by negative 2 to the power n, and so that will leave us with 4 lambda minus 8 lambda plus 3 lambda equals negative 5. Sorry, 5, not negative 5. So we'll get rid of that negative. So 5. So that then gives us negative 4 lambda plus 3 lambda. Negative lambda equals 5, which means that lambda equals negative 5. Okay, so now we've got the value of lambda. We've got a particular solution, PS, of an equals lambda, which is negative 5. So negative 5 times by negative 2 to the power n. Now we use the initial conditions to work out the value of the constants. So we'll start with a0 equals 2, which means that n is 0. So let's get substituted into the general solution. So let's just highlight our particular solution there. So our general solution is going to be the complementary function plus the particular solution. So a n, let's just write it down here, our general solution, a n equals a times by negative 3 to the power n plus b times by negative 1 to the power n, then plus the particular solution, so plus negative 5, so it's actually minus 5 times by negative 2 to the power n. So I thought I'd just put this here because this is what we're going to substitute into. Right, first substitution, a0, 2 equals a times by negative 3 to the power n, which is 0, plus b times by negative 1 to the power n, which is 0, minus 5 times by negative 2 to the power 0. Now what happens is all of these power zeros make it 1. So we have 2 equals a plus b minus 5. So adding 5 to both sides, we'll have a plus b equals 7. Okay, so this is our first equation. What do we need to solve it simultaneously with? Well, a1 is negative 1. That means n is 1. So we'll substitute that in. So we'll have 1 equals negative 3 to the power 1. Whoops, I missed the a out. So a times by negative 3 to the power 1 plus b times by negative 1 to the power 1 minus 5 times by negative 2 to the power 1. Okay, now what happens with this one? Well, all the power 1s are just will just be the number, so I'll have 1 equals negative 3a minus b plus 10. I've just realised this should be negative 1 here because a1 is negative 1. So that will leave me the equation, let's see, 3a plus b equals, so the 10 will be there, that negative 1, which I've just corrected, negative 1 there and there. That'll become plus 1, so that's 11. Right, so I need to solve these simultaneously. So you can do this manually or use your calculator. Whichever way we do it, what we will get is A equal to 2 and B equal to 5. Right, we can now write our particular solution, which is basically now our final solution, what we have written here, but with our arbitrary constants. So we end up with an equals a, which is 2, so 2 times by negative 3 to the power n, plus b, which is 5, times by negative 1 to the power n, minus 5 times by negative 2 to the power n. So there we go, there's our final solution. We got there eventually, so let me just highlight that so that we can see clearly where it is. So there's our final solution for this question. Okay, so we just need to find a general solution to this, not a particular solution. So we'll start first of all with the associated homogeneous recurrence relation, and that is Sn equals 3 Sn minus 1 plus 4 Sn minus 2. So from there we want to find the auxiliary equation, or form and solve the auxiliary equation. So that will be r squared. Now what have we got here? So that would be the value of a, which is 3. That would be the value of b, which is 4. So r squared minus ar, or 3r, minus b, so minus 4 equals 0. Now this can be factorized like this, and it's going to be 4 and 1 and minus 4 plus 1. So we have r equals to 4 and minus 1. So my roots are equal to, I call alpha equal to 4 and beta equal to negative 1. Since I have two real roots, the general solution is going to be of the form a alpha to the power n plus b beta to the power n. So let's just substitute those values in, and this will give me my general solution to the auxiliary equation, which is the complementary function. So the complementary function will be Sn equals a times by 4 to the power n plus b times by negative 1 to the power n. So we'll just put a box around that so we can see that later on. Of course, we'll need to add this to our particular solution once we found it. Okay, so for our particular solution, we need to look at the form of g of n. Now the form of g of n is this form, kp to the n, and k would actually be 1 in this case, p to the n, but we have something that looks like that in the complementary function, because this p would be 4, wouldn't it? So actually this is like k times 4 to the power n. That appears in our complementary function. So normally we would say, right, try lambda p to the n, but this is like lambda p to the n. Okay, So since we have something like lambda 4 to the n in the complementary function, we try, and we got multiplied by n, lambda n times by 4 to the power n for the particular solution. So this is one where we need to multiply our form of the particular solution by n, because this appears here. A constant times by 4 to the power n, a constant times by 4 to the power n. Okay, so first thing we're going to say is that Sn equals lambda n to the 4n. This is going to get substituted into the recurrence relation here. So we'll have lambda n to the 4n equals, now it's 3 times Sn1. So everywhere I have n, let's underline it, is going to become n minus 1. So you need to take care when we write this out. So it's going to be 3 lambda n minus 1 times by 4 to the power n minus 1, then plus 4 lambda n minus 2 times by 4 n minus 2, I'm not sure I write minus 1 there, it should be 2 times by 4 to the power n minus 2, and then plus 4 to the power n. Now the only way I'm going to go about simplifying this is when I can get these powers the same. I'm going to get these all to the power n. So if I take a 4 out of this and put it here, I can write this as 3/4 and increase this by power 1, so it becomes 4 to the power n. I can take that 4, put it here, that will become 4 to the power n minus 1. Take another 4 out, so make this a quarter, and then here I'll have 4 to the power n. So what I'm going to have is something that looks like this. Lambda n times 4 to the power n equals 3 lambda, or sorry, 3/4 lambda, write that down, 3/4 lambda n minus 1, 4 to the power n, then plus a quarter lambda n minus 2 times by 4 to the power n plus 4 to the power n. Right, next thing we can do is divide everything by 4 to the power n. Okay, so they're all going to go, actually that'll just become the number 1. Then we'll expand the brackets. So the next thing that we'll have is lambda n equals 3/4 lambda n minus 3/4 lambda plus a quarter lambda n minus, and then a quarter times 2 is a half, so minus a half lambda plus 1. Right, then the next thing we can do is to simplify it. So you've got lambda n on the left, then we've got this 3/4 lambda n plus a quarter lambda n, which is 1 lambda n. And then we've got minus 3/4 lambda minus a half lambda, so that's minus 5/4 lambda plus 1. Now we can take lambda n away from both sides, so that just leaves us this equation, that minus 5/4 lambda plus 1 equals 0. So that means that 5/4 lambda equals 1. So times both sides by 4, divide by 5, so we'll get lambda equals 4/5. So now we have our particular solution as lambda n times by 4 to the power n. So that's going to be lambda, which is 4/5 n times by 4 to the power n. There we go. So now our general solution is going to be those two bits put together. So we'll have Sn equals, now we only need to give the general solution, so a times by 4 to the power n plus b times by -1 to the power n plus our particular solution, so plus 4/5 n times by 4. to the power n, and we leave it like that because, as I said, we've not been given any initial conditions, so we don't need a final solution. We just leave our general solution in that form. Right, you should now be able to do exercise 4C on pages 140 to 141. And just a quick recap here, because you can always go back to the first slide and have a look again. So we are looking at recurrence relations, second order recurrence relations like this. If it's non-homogeneous, we solve the homogeneous part. We're either going to have two real roots, one real root, or complex roots. Now remember, there are two forms that we can write the complex answer in, and one of the forms actually is the same form as what we'd use for one real root. And then if it's non-homogeneous, so we need to find a general solution for this, then these are the forms that we look at for the non-homogeneous part, and these are what we try for the particular solutions. Now if you see something of this form in the complementary function, then you would times it by n, so times by n. And if something of that form also occurs in the complementary function, then multiply by n squared.